Hello everyone, I am Bhowmick-Saha and welcome to my Capstone project for the audio-to-MIDI music transcription deployed in Google Cloud. So why music? Why AI? We know AI can write emails or summarize documents, but could it transcribe a Beethoven recording into digital sheet music? This project aims to explore that question. I chose this use case because it blends creativity with AI and allows for a lot of innovation. Let's hear a small clip of a music which I used for my experimentation. This is great. So, what if we can transcribe this music in real time? Let me share my screen. So, you heard a piano music. And here in the screen, you can see a visual representation of the MIDI file associated with this MP3 file that we just listened. For this project, I used the Maestro dataset, which pairs high-quality piano recordings with aligned MIDI files, making it ideal for supervised learning. Each black bar shows when a piano key was pressed and for how long. This is known as a piano roll. It's essentially a 2D matrix where time flows from left to right and pitch increases from bottom to top. This MIDI data is used as the ground truth label to train our AI model. Later, we will compare this with what the model predicts from just the audio. What if? If we could press play on any song and instantly see the sheet music appear live in real time? This is the magic we are aiming for. The use case, why it matters. This is called audio to MIDI transcription and it has exciting applications. Music educators can analyze performances, creators can remix classical works, and music search engines could work based on melodies, not just text. Let's talk about the challenge, why it's hard. Music is not like text or images. It is complex. It has layers, multiple notes at once, rhythm, harmony, variations. And it changes over time. So transcribing it is a deeply temporal and multidimensional AI challenge. So how we should teach an AI to listen like a musician? That's where our journey starts with audio signals, spectrograms, and a bit of cloud magic. As part of my ML AI capstone, I chose to tackle a creative and technical problem, translating piano music into MIDI using deep learning and generating insights using generative AI. So the overview is this slide summarizes what I built. An end-to-end system that turns music into structured insight using AI and cloud. So step-by-step flow, matching the diagram below. MP3. I started with raw piano recordings in MP3 format Each audio file was digitized and processed into log-mel spectrograms using Librosa. Neural net. I trained a convolutional neural net model to convert those spectrogram slices into piano roll representations. Essentially, what notes are being played and when. I also experimented with classical ML like SVM for comparison. The MIDI. The output was converted into structured MIDI file, a digital representation of sheet music. This could be visualized or even played back as synthesized audio to check what I predicted and how it compares with the original audio. Then the summary. I used a GenAI model, specifically Gemini, to generate a natural language summary. What kind of piece is this? What mood does it evoke? Things like that. Now the entire thing is integrated in GCP. Everything was built and deployed on Google Cloud using Vertex AI, Cloud Functions, and Google Cloud Storage, making it reproducible and scalable. Before diving into machine learning, we first visualize the raw audio. What you are seeing here is the waveform. It shows how the sound intensity changes over time. This file is a 21-minute piano performance sampled at 22,050 data points per second. Each peak and valley represents the loudness of notes or silence. But this raw wave diagram isn't very interpretable for music structure. So we next convert into a log-mel spectrogram to capture both pitch and time context. So now let's move on to the key steps to digitize the MP3. Once we load the MP3, we resample it to a standard 22,050 Hz to make training consistent. Then we convert the raw waveform into a MEL spectrogram. This gives us a 2D matrix where each row is a frequency and each column is a short time slice of the audio. This MEL spectrogram becomes the input to our CNN model, just like how image pixels are input to the image models. So here you can see that I have provided a path to one audio file in our local environment. It chops the waveform into short overlapping time windows, and for each frame it finds how energy exists in 128 frequency bands. Compute the MEL spectrogram with 128 MEL bins or bands. What does 128 represent? 128 means there are 128 different frequency channels being captured. So here you can see an MP3 in numeric representation. So what does 128, 54,096 mean? 128 means MEL frequency bands. This breaks the audio into 128 pitch-related frequency bands aligned with human hearing. And 54,096, this number means number of time frames. Each time frame is a tiny snapshot of the audio. So together, this spectrogram is like a matrix of sound intensity across pitch and time. It's a heat map of musical energy. How to interpret it? We can think of this as a 128 frequency of 54,096 time frame image. This is what the model sees when listening to a song. This is a MEL spectrogram visualization. So MEL spectrogram is a visual fingerprint of sound. On x-axis there is time and frequencies are on the y-axis. Colors show how strong the sound is. MEL stands for MEL scale, which mimics how our ears perceive pitch. 0 dB means loudest, negative means softer, and more negative means quieter. Why this slide is important? To build a supervised ML model, we just don't need audio, but also the labels. The MIDI file is what gives us the ground truth. The notes being played, when they start and end, and how hard they are played. What is shown in the code is we are using Pretty MIDI library in Python to read and parse the MIDI file. First, we list all instruments. The file only has a piano track, which is great for our training. Then we extract the first 10 notes from the piano roll. What's in each note? Each note has a pitch. For example, 74 represents D4 or D5, a start and end time in seconds, and velocity, which represents how strongly the note was pressed. And why this matters for ML? This structure is what we use to create our Y training labels, either as piano rolls or as single note summaries. It also helps us understand how dense and complex the music is. This file has over 12,000 notes. Key aspects of this project: transcription. Transcribe audio into musical notes using deep learning. We start with an MP3 piano recording and convert it into a visual form, a spectrogram. Then convolutional neural network or CNN learns to predict which piano keys were likely played at each moment. It's like teaching AI to read sheet music by looking at sound. Then comes feature engineering and ML. Extract and summarize music features with classical ML techniques. Alongside deep learning, we use traditional machine learning to extract things like tempo, rhythm strength, and pitch patterns, which are easier for humans and models to interpret. This gives us a high level music summary. Music understanding. Use LLMs, for example Gemini, to describe the mood and structure of the music. Once we have a digital summary of the music, we use a large language model, Gemini, to describe it in natural language. It can label the mood like melancholy or joyful and even describe the complexity of the music. MIDI generation. Generate playable MIDI files using AI predictions. The AI's note predictions are saved as MIDI files, which are digital sheet music. These can be played back with virtual instruments so we can hear what the model thinks the sound sounds like. Cloud native deployment. It is built and deployed entirely on Google Cloud Platform. Vertex AI, Cloud Functions, GCS, all this is built and deployed on Google Cloud. The models run on Vertex AI. Inputs and outputs are stored in cloud storage, and automation happens through Cloud Functions. That's the service. It is fully cloud native and scalable. How the system works from audio to intelligence. So raw MP3 is the audio. We start with an MP3 audio file, say a piano performance from the Maestro dataset. Then comes audio feature extraction using Librosa. We convert this into a spectrogram, essentially a heat map of sound over time and frequency. This is done by using Librosa library in Python. Deep learning prediction using CNN. A CNN model architecture interprets this spectrogram to predict which notes are likely being played over time, resulting in a MIDI piano roll. MIDI synthesis. So pretty MIDI plus fluid synth. We take this piano roll and synthesize it back into playable music so we can compare or hear the results. There is a disclaimer. It didn't work out very well for my experiment, so I didn't use it as a benchmark. Music summary and mood detection. LLM, Gemini. We summarize the music, what kind of emotion or structure it has, using prompts to Gemini to describe it in natural language. And the way it works is Gemini looks at the MIDI output and it predicts the mood of the music. Feature engineering and ML. We also explored classical ML models like SVM using handcrafted features helpful for interpretability or simpler tasks. Cloud deployment, Vertex AI, GCS, and cloud functions. Now let's talk about the modeling, what I did for feature extraction. We start by converting the raw audio into something a model can understand. That means extracting numerical features from the waveform. Male spectrograms are key here. They represent how the sound energy is distributed across frequencies over time. We also add other features like MFCCs, spectral centroid, zero crossing rate. These are all known to help capture tone, rhythm, and energy of the audio. Classical machine learning models. Once we have structured features, we try traditional ML models like SVM, random forest. These models are simpler and easier to interpret, which is helpful in benchmarking and early experimentation. We use them to predict the most frequent MIDI note or high level musical attributes in the music. Deep learning models. To go deeper into time dependent patterns, we apply convolutional neural networks. CNNs look at the spectrograms like images, capturing local patterns across time and frequency. We tune the architecture, layers, and activation functions to improve MIDI prediction accuracy. Let me get started first with how I tried to handle this complex use case using classical machine learning model, for example, SVM. Let me talk a little bit about the usage of SVM model over here. It's about predicting the most common note in this use case. Why SVM? Because it is good at small sample, high dimensional tasks. It's easy to interpret and benchmark early performance. In addition to deep learning, I also explored a classical machine learning approach using support vector machines, SVM, a reliable and interpretable algorithm for classification tasks. Here, the task is simplified. Instead of predicting the entire piano roll, we just predict the most common note being played in a slice of audio, kind of like identifying the dominant pitch at a moment in time. Label generation. First, I created labels by scanning each piano roll slice and picking the most common frequent MIDI note in that slice. This turns it into a single label classification problem. Then the feature flattening. Then I flatten each log-mel spectrogram from 2D 128 frequency bands times 100 time steps into one-dimensional vector, resulting into 12,800 features. Then comes the scaling. I normalized these values using standard scaler. so the SVM model doesn't get thrown off by different ranges in the data. PCA. Since 12,800 features is too much for classical model like SVM, I applied PCA to reduce dimensionality and speed up training without losing too much of information. Pipeline. Finally, I used scikit-learn pipeline to wrap all of this into a reusable, reproducible training pipeline. This makes it easy to tune and deploy. This is a great example of how even classical ML can be powerful in the right context, especially when the problem is reframed and simplified. Let me go into how I used CNN model to predict the music transcription. Now, why CNNs? We use CNNs, a type of deep learning model originally desired for image processing. But why does that work for music? Because we convert audio into spectrograms, which are essentially images, and show how frequency content changes over time. What you see on the right is a CNN architecture which I used. You can see the input shape 128, mel bands by 100 time frames. That's the spectrogram chunk we feed in. What the model learns, each conv 2D layer applies filters to this spectrogram, looking for patterns just like how it would in an image. It learns edges, transitions, texture, and pitch changes, all of which relate to musical structure. Once I had a CNN architecture, the next step was tuning it to improve performance. This slide shows how the results of 5 different model experiments and where I varied some key hyperparameter values. Each row represents one experiment with variations in filters. Filters are essentially the number of convolution filters per layer. More filters equal to more pattern complexity. Kernel size, how wide the filters are. For example, 3 by 3, 5 by 5, 3 by 5. Dropout rates controls the overfitting. Higher dropout drops more neurons. Dropout is a regularization technique used for training to prevent overfitting. It randomly drops out neurons. That is, if it sets to 0, then it hasn't dropped out any neurons. If it sets to higher values, then it has dropped out more number of neurons. For example, you can set it to 0.3. That means 30% of the neurons will be dropped. 0.5, 50% of the neurons will be dropped. 0 means no dropout. Then comes the learning rate, how fast the model learns during training. I evaluated each of these experiments and have two sets of evaluation metrics. So test accuracy, how many notes the model correctly predicted. But this is a weak metric here because of class imbalance. Test loss, binary cross entropy loss, better for capturing true performance when predicting many notes at once. As you can see, accuracy is quite low overall, which is expected in a multi-level music prediction task where many frames are empty. Experiment 3 gave the best performance. It's the best trade-off between complexity and test loss. So I used that architecture moving forward. You will note that test accuracy is low across the board. That's expected in a music prediction task like this. It is complex task. Since most time frames don't have any notes being played, the model could guess no note most of the time and still look accurate. But what we really care about it is, did the model catch the right notes when they were played? For that, I plan to look at F1 score and precision in future, which are better suited for this kind of prediction. This slide gives the comparison between true versus predicted MIDI quality. Here you can see a comparison between the original MIDI notes used in real music and what the model predicts. The true distribution shows a natural widespread across many pitches, typical of expressive music. In contrast, the predicted notes are much more concentrated. A few notes are repeated thousands of times. This suggests the model is learning shortcuts, favoring specific pitches rather than understanding the full musical structure. Fixing this, I think, will require better training. Training with very simple music, for example, just like how a child can learn with simple music and notes associated with it for supervised learning. The other approach is you can play music in noisy environment and see what it can capture, what it can predict. Now, since we already talked about how I used SVM and CNN, let me talk a little bit about how I tried to experiment with LSTM model. LSTM is long short-term memory networks, which are designed to model sequences, exactly what music is. Unlike a single static image or tabular row, music unfolds over time. At time t, the model needs to remember what notes were sounding at earlier frames in order to decide if a note is still holding, if a chord has shifted, or if a melodic line is continuing. LSTMs maintain a memory cell that can carry information forward many time steps so that they can learn patterns. Like this note was on 50 frames ago and should still be on, or that chord progression happens every 8 beats. There is a variable length context in this use case. So even if the input slices are fixed to say, for example, 100 time frames, musical events sometimes span longer or shorter intervals. By using an LSTM, we allow the network to adjust how much past context influences the current prediction, rather than forcing it to treat every frame pair independently. Frame by frame transcription. When we slice a spectrogram into overlapping or non-overlapping chunks, we still need to predict an 88 by 100 piano roll output. 88 represents possible MIDI pitches and 100 is 100 time steps. An LSTM layer, especially when wrapped in a time-distributed dance or a sequence of LSTM cells, can cascade through those 100 frames, making a binary on-off prediction for each note in order, preserving the order of events instead of flattening everything into one big vector. Smoothness in the output. Purely CNN approaches might struggle to keep note onsets and offsets consistent across frames. sometimes blipping a note on for one frame, then off the next. The gating mechanism inside LSTM helps enforce temporal smoothness. If a note was on in previous steps, the LSTM cell can carry that information forward until it confidently sees evidence of an offset. Let me share my screen to show how LSTM architecture worked and a sample LSTM architecture that I used for my modeling purpose. Here is our sample LSTM transcription model. Let's get into a little bit of LSTM architecture. LSTM has three different gates: forget, input, and output. This architecture helps the network decide which information to keep and which information to discard at each time step. There are two types of temporal memory, short-term and long-term memory, and they are called hidden state and cell state. Generally, cell state is represented by CT notation. It is a long-term memory. Because of the cell state CT, the LSTM can carry information such as I saw a C chord 5 frames ago, or this is part of a repeating motif. HT generally represents short-term memory of CT that is passed forward. Stacking LSTMs allows learning hierarchical temporal patterns. For example, a two-layer LSTM can learn more abstract sequence features than a single-layer LSTM. Time-distributed dense function simply means apply the same classifier to every time frame independently so you can get a sequence of outputs. At each of the 100 frames, the time-distributed dense layer guesses which of the 88 keys are on. In other words, it's a multi-level prediction. Multiple notes can fire at once, not just a single most likely pitch. Output shape. A piano roll patch with 100 time steps and 88 possible MIDI pitches per step. In music transcription use case, we feed in a 2.3-second log-mel snippet, 100 frames of 128 band spectrogram, and pass it through two stacked LSTM layers with dropout in between. The time-distributed dense wrapper is when your target is a sequence, for example, a piano roll of shape, which I mentioned just now. You often want to apply the same dense, fully connected neural network layer to each time step independently. It produces 88-dimensional probability vectors at each time step, which we threshold to get our binary piano roll. So let's put it all together. Here is a step-by-step recap of how the LSTM plus time-distributed layers operate on one training example, for example, a slice. So log-mel spectrogram input slice, suppose a single slice has shape 100 by 128, that is 100 time frames, each with 128 dimensional MEL spectrogram vector. First LSTM layer reads 128 units and return sequence equal to true, which means that it reads 128 dimensional input and its own past hidden state, initially zeros for H0 and C0. It uses the forget, input, and output gates to update the CT and HT. Because return sequences is set to true, we collect all 100 hidden states into a tensor of shape 100 over 128. Dropout rate is 0.3. It randomly zeroes out 30% of those features during training to prevent overfitting. Now let's talk about the second LSTM layer. It has 64 units and return sequences set to true. It takes the sequence of shape 100 over 128 from layer 1 and again gets through to produce a tensor of shape 100 over 64. Dropout rate is again 0.3. Then comes the time distributed dense with activation function sigmoid. For each of the 100 time steps, take the 64-dimensional HT vector and pass it through a fully connected layer with 88 outputs plus sigmoid. That yields 100 by 28, where each of the 100 rows is a probability for each of the 88 piano keys at that frame. So during inference, we feed one slice of shape, which is 1 by 100 by 128. 1 is for the batch dimension, and obtain a 1 by 100 by 88 probability map. Thresholding at 0.5 produces a binary piano roll of shape 100 over 88. I ran a grid of LSTM configurations, varying the number of layers, hidden units, and dropout rate. Lowering the learning rate and adding a third LSTM block gave us the best validation F1 while keeping the loss down. Early stopping on validation loss prevented overtraining. Let me go into how I used CNN architecture to predict the music transcription. Now, since I already spoke about the classical ML and the deep learning aspects in this project, I will move into the generative AI capabilities which I leveraged for this project. Generative AI capabilities. Let me highlight how this project taps into multiple generative AI capabilities, not just model training, but also creative evaluation and orchestration. So, audio understanding. We started by turning raw audio into structured spectrograms. These spectrograms are then used to extract embeddings, compressed, learnable representations that feed into downstream models. Function calling. We use Vertex AI and GCP Cloud Functions to operationalize model predictions. In other words, we are using AI endpoints in real time, just like agents do. GenAI Evaluation. After predicting the notes, we bring in Gemini, a large language model, to describe the style and emotion behind the music. Bonus, vector storage. The embeddings are saved in GCS. This opens the door for future experiments, such as searching for similar songs using vector similarity, a common use case in music recommendation engines. Let me show you a quick demo. Here is an MP3 file from 2018 in Maestro dataset. First, we extract features and send them to the CNN model hosted on the Vertex AI. The output is a piano roll prediction. Next, we use the SVM model to identify the most common SVM, most common MIDI note. Finally, we call Gemini with a custom prompt like describe the mood and style based on the note pattern. And here is what we get as response. Most common note, so the most common note is 10 over here in this use case when I fed an audio MP3 file with a piano music. Let's look at the Gemini caption that it generated. A dense tapestry of piano notes, a whirlwind of sound where every key finds its voice, a sonic exploration of the instrument's full range. And let's see what the mood is for this music. It is energetic. So this is the Gemini magic done on the predicted piano notes by the CNN model. Since we covered all the modeling aspects that I used in this project, now I will move into the software engineering part of it. How I deployed these models into Google Cloud, what are the steps that I took, and what are the Google Cloud services that I leveraged. This is the sample model inference pipeline. Let me walk you through the high-level architecture of how this system works, all built on Google Cloud. Data source on the left is Kaggle. We started with a Kaggle dataset containing raw piano MP3s and their corresponding MIDI files. That gives us both the sound and the ground truth notation. Cloud storage bucket is on the center left. This data is stored in GCS bucket. All the audio files, training, test data, models, all are stored over here. That gives us like a data lake in Google Cloud Storage. Then on the right is the Vertex AI. We have Vertex AI where the actual model training and deployment happens. From experimentation in Jupyter notebooks to model registry to endpoint deployment. Cloud Functions is in the middle. That is the service layer. So Cloud Functions is the serverless backend infrastructure of Google Cloud. It takes an audio input from GCS and sends it to the model in the Vertex AI to get the prediction, and it returns the MIDI notation as prediction. Now the governance. IAM handles access control, who can invoke what, and cloud logging helps with observability. That means we can track and audit how the system behaves in real time. This end-to-end setup shows how a creative AI use case, audio to notes, can be fully automated and served in a scalable way using GCP tools. At this point, I have covered the data engineering, the modeling, the deployment, and MLOps, some sort of MLOps part of this project. Now I will wrap up this presentation with reflecting how I started my journey, how the journey looked like, and what are the plans for future improvements. So it's about starting from unfamiliar territory. Coming from a background in text-based data, working with music felt completely new. Unlike labeled rows in a table, audio is continuous, layered, and hard to visualize, which made me initially overwhelmed. Finding a way in, I began by doing focused research to understand how sound can be converted into numerical formats, like spectrograms and piano rolls. That gave me the foundation to start the experimentation. Complexity of real music. The raw piano performances in the dataset were long, expressive, and nuanced. In hindsight, starting with simpler, shorter audio clips could have helped me build confidence before taking on complex compositions. But the problem is finding the right data source. Given the time constraint, I had to pick the data source which is readily available in Kaggle. Visualization gaps. One of the biggest challenges was seeing what was happening in the audio features, in the MIDI structure, in the model's predictions. Lack of intuitive tools made debugging harder and progress slower at first. Future work to improve accuracy. Sequence modeling. Music is inherently sequential, so RNNs or LSTMs might do better. I did dig a little bit into the LSTM models, but I believe that more digging, more working, and more spending time with the LSTM models will give better performance. Transfer learning. Just like we used pre-trained models for images, we can use pre-trained architectures like ResNet on spectrograms or other models trained on music datasets to give our model a better starting point. Audio embeddings. Models like CLAP can convert audio to embeddings that capture tone, rhythm, and mood. We can then use transformers on those embeddings to predict MIDI with more context awareness. Better data engineering. Finally, just improving how we prepare the input, how we slice the audio, clean the MIDI files, or post process predictions can often lead to meaningful gains. Future enhancements for automation. Once a model is deployed, the real challenge begins, keeping it accurate and aligned with real world changes. We plan to automate retraining, implement model monitoring, and build feedback loops into the system. This will help our models continuously improve, reduce technical debt, and potentially evolve toward reinforcement learning frameworks. Thank you very much for watching. And I have provided the QR code for my Medium article, which I published, and the GitHub public repository. So this is an open source GitHub repository. Please feel free to look at it and contribute. Okay, before I wrap up, I would like to extend my deepest gratitude to my advisor, Viviana Marquez, for her unwavering support, timely feedback, and invaluable guidance throughout this Capstone project journey. Her insights, both technical and strategic, helped me navigate challenges, refine my approach, and get the most out of the MLAI certification course from UC Berkeley. Thank you.